The talk today is going to be about a generic approach to heterogeneous containers. Vicente, with his experience on cooperating on the C++ standard and Boost libraries, surely knows a lot about that. He currently works for Nokia France. Let's welcome Vincente Botet with his talk, Product Types.
Hello to everybody. My name is Vincente Botet, and I work for Nokia in France, in Lannion, a little town in the Brittany on the far west. What I will present today is what could be the state of the standard on C++ 20 for product types. How do they could look like? We'll see first what is the problem, what are product types, how do we access product types in C++ 17, how could we maybe access them in C++ 20, some algorithms that work well with product types, and more examples, more algorithms that need some additional constraints on the types. We'll finish by work that I plan to do and a conclusion. So, what is the problem? Given this trivial structure for a point on 3D, how you ever see some code like this one? Have you ever wrote a code like this one? Yes? It's funny, no? Or like this one. We want to stream, or we want to transform to a string. The things are quite similar. And what happens if now we define a point 3D as a tuple? We could define then it using the accessor stdget, and we see that this code is less friendly, it's less readable, but it has the advantage that it works also for std array or for C arrays, if we have the customization for them. Well, but the things are not so simple, because what we want is to have a generic algorithm in order to do that for all the types that follow the tuple-like access. Upper side, we can see the definition. We will insert a left brace. We call an auxiliary function. We insert the right brace. And the function, the auxiliary function, is a function that it is defined recursively using metaprogramming. Because we have that the index of these elements are known at compile time. Then it is just implementation with a C++ 98 style. What we have is that on the default case, we will add a command if the index is different of 0, and we will just recall to get and insert it on the stream. And we recursively call with the next index. At the end, when the index are reached, the last element is reached, we do nothing. Okay, what are product types? Wikipedia tells us a product type is a type that is compound of other types. And we preserve the order of these types. The reals and reals square, it is a product type of real times real. We are used to this kind of things, and it is good to see that things that we have learned on school, we can rename them on programming. Here are some standard types that we have, like a product type. Do you know of others that could fall in this category? We have std array, std pair, std tuple. Of course, we have the same for boost. We have also compressed pair, that it is a product type with an optimization, but a product type. And we have, because some of them are homogeneous, have the same type, and other are heterogeneous, contains different types. The C arrays and std array are homogeneous types, and the others are heterogeneous. There is also something that it is important, is that some product types, we have like a type constructor that we can change the type and we can change the number of elements to build other types. That is, if I have an array of ints with 3 elements, I can also think of an array of strings with 2 elements. I can change both parameters, and we'll see that this is useful for a lot of algorithms. Okay, let's see the kind of access we have today for these product types. We have the well-known access to the fields of a structure. We have the access by index to an array. We have the well-known also tuple-like access with the get function, the tuple size and tuple elements threads that are specialized for the specific types, and the standard provide a specialization for these 3 types. And we have a last feature that had been added to C++17 that is called a structure binding, and it is a feature that will help us a lot to extract the contents of a product type. Okay, just what I said, and we can define the get function for a C array. The standard don't define it, and I believe that we could add it without any trouble, and make C arrays behave as a tuple-like type. And there is one minor issue, is that C arrays will not be found by overload, because there is no type that will be associated to the parameter. No namespace associated to the parameter, and we need to introduce the function std_get before calling it. This is an idiom that it is used currently on the standard library for swap or other customization points. Okay, structures in general are product types. We have here an example of a structure A that has 2 elements, X and B is again another product type with 2 elements, E and G. What we have is that we need to specialize for each one of the classes the tuple-like access. And there are a lot of libraries that have defined some kind of product type access, and they have defined some macros that will generate this specialization. Two examples of these libraries is Boost Fusion and Boost HANA. And we allow to, given an existing structure, to adapt it, or even we can define one structure directly, defining what are the elements of this structure. This will define the structure and also will define some accessors to make it possible to have generic programming with these structures. The main problem is that each library is defining a different access. And what we need to make it possible to build on top of all these types is a unique access. Okay, structure binding. What we have is that given a point, for example, we are able to extract with this new statement, we are able to extract the fields in variables x, y, z. We can extract them either by copying or by reference. There are a lot of other variations. I will not insist. But this is a feature that is quite friendly for the user. It is very easy to extract the contents of a structure and give names that are meaningful for the user. We can, using this structure binding, it becomes very easy to define functions that have multi-return values and extract them in an easy way. Then if f is a function that returns two values, int and a string, then we can just use this syntax in order to get the two values directly. And in addition, what we have is that with the range-based for loop, we accept also that we iterate on a container that contains this kind of types that support structure binding. And this is, I will say, quite funny. It's readable. It is short. It is, I will say, it allows to write good code understandable. Then structure binding works for C arrays. It works also for any type that has been customized using the tuple-like access protocol, and works also for types that have all his non-static data members public. Okay? Why only for these types? Because we are really, this is something quite intrusive. We are extracting information from the type. It is good that we do that only for types that have these members public. In addition, as we have for aggregates, we are able to access the members that are bit fields with the same syntax. There is no problem. We have access to bit fields using this structure binding syntax. The problem is that we cannot customize bit fields with the tuple-like interface. Can someone say why we cannot customize get for bit fields? I will say because a bit field has no address. And get, what it returns is the address of the field. Then we cannot customize a bit field using get. However, a structure binding allows us to extract them. We will try to see if using a structure binding we are able to take in a product type and try to transfer this product type to a steady tuple. Okay? We will define a function as tuple, and what we can do is to define a tuple once we know the number of elements, because the syntax of the statement of a structure binding, it works for something when we know exactly what the number of elements. Then a structure binding is good, very good at the user level, but we cannot write generic code no more than that, because we need this number of elements. Then we need something else. Just a summary, a structure binding very well at the user level, tuple-like access, not so friendly, but generic. Okay, we'll see now what we have on proposals that are ongoing on the committee for C++ 20, who knows. There is a pattern matching proposal that its main goal is to manage with variant types, but that works also for product types. There is another proposal that is on some kind of extensions of the parameter packs in order to make it possible to have types. We'll say a little more detail. There are other proposals that want to define operators to get access to these elements, to have a syntax that is shorter. And there is a product type proposal that just want to cover all these types using a different name. And that will work for the same types that a structure binding. We have the pattern matching, allow us to inspect the value of a variable, and in case this variable is a product type, we can get the values as we have for structure binding. This is quite similar. The mechanism is this much more general, but in the case of product types, we have the same thing. However, in order to have this access, the proposal requires that we have a specific operator that it is defined for these structures. I will not enter on details. The idea is give me the address of the field, and this will introduce another customization point, and we will need to ensure that both customization points are the same. Packs types. You know that currently in C++ 11, 14, 17, we cannot use parameter packs everywhere. And this proposal is trying to extend where we can use these parameter packs. And one case that it is not allowed today in C++ 17, it is to define n fields. The t dot 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 t, here it is defining n fields, each one having a specific type, okay? And this is a sample way to define a tuple. It is a structure that has T replicated for each one of the templated parameters. One important thing, I believe that this is something that we are looking for since a long time ago, is to be able to name the type associated to an aggregate initializer. Today, we have, who know here what an initializer list is? Initializer list, okay? An initializer list is something that looks like an aggregate, but all the values are of the same type. An aggregate can have different, the values could be of different types. Then this proposal proposed to give this type int char_const pointer. And I believe that it is something that we are missing. We don't have a name for the type of this expression. And this proposal is giving it a name. Then we can define functions that return several values. And we can use this function, calculate target coordinates that returns 2 double. And we can define a function launch, for example, that calls to another function, and that we will use the pack expansion operator, the ellipsis operator, to expand the elements of returned by this function. This is something that is quite useful, and you can see on the bottom the equivalent using the current standard. We need to return a tuple or a pair, and we need to use the function std_apply that will unpack the elements of the tuple returned by the calculate target coordinates function. Then this proposal, literal packs, is a proposal that make, I will say, we need to have less libraries in order to say the same thing. Okay, again, a new syntax for defining things, but we need always to customize, to say how this operator, ellipsis operator, expansion operator, works for user-defined types. And the proposal, it is yet in a, I would say, in a draft state concerning this point. He suggests to have an operator like this one, but this again introduced a new customization point, and the proposal, it is not clear how all this works with CRAs or sample structures. Again, the interaction between this expansion operator and this parameter, the template parameter expansion, it is not yet analyzed. Then we don't know, because maybe we will have to use twice the ellipsis operator. And because we want everything, not only we give a name of each one of the types, but as with a struct, we can give a name of the field. Okay? And this is the same thing as an anonymous struct, a struct that has not a name. Difference is that this is new on the language, and we don't have any backward compatibility issue, and an anonymous struct in C++ from the beginning has a specific meaning that make it not very usable. We cannot return it from a function because an anonymous struct is different from another anonymous struct with the same syntax. Crazy, but this is C or C++. The third proposal just provides some operators that will have make maybe easier to get the elements and to get the size of a parameter of a product type, and also some way to unpack a product type. And this proposal is in some way based with the Python syntax about the packs, and he proposed also to have some kind of slicing to be able to take elements from 3 to 7. Okay, I will repeat. Then for me, a product type, it is something that is supported by a structure binding. The same feature, the same kind of types, and a type that is not supported by structure binding is not a product type. Currently, in the standard, we have algorithms as, for example, tuple cat, std apply, construction from tuple, that works only for some specific std types. And these algorithms should work for all the product types, for all the types that support a structure binding. I believe that the pack type is something that is quite powerful, but it is not clear yet how it will take into account all the types covered by a structure binding. Then we can define an interface that will be able to get any element of a product type, have its size, and get the element type. And I have used a namespace product type in order to be explicit about what these operations are about. This operation, get, it is not get of anything. It's get an element of a product type. And I believe that being explicit here, it is much better because we have today in the standard that get is also used in order to get an element of a variant type. What is in boldface? It is what the compiler should provide. The compiler should provide a specialization of the type. Okay, and on the library side, we can do something else, remove the const, the volatile. The same for the access to the element. And we need to provide us, using some kind of reflection, access using the get function. I have also added an element sequence 4 that it is quite closer to the index 4 that will give us the index for all the elements of the product type. We'll see that we will use this. This is just an alias that give us something shorter. We have product type that require 3 operations: get, size, element. And we have a lot of things that can be done for this kind of types. We can do a swap. We can, of course, do apply. We can do a stream insertion. We can do apply a function for each one of the elements. Copy. We can fold, also apply a function accumulating a value. We can compare also using the lexicographical order, and we need to write these functions only once for all these types. Here it is, these functions will be structured always the same way. On the bottom, we have the function apply its parameters, and we will use an auxiliary function, apply EMPL, to which we will pass the index of this product type. If we have a product type with 3 elements, we will have a sequence of 0, 1, 2. This sequence of 0, 1, 2 will be passed on the top, and as we have a parameter pack, we are able to expand on it. And then we will use the pack expansion for the expression, give me the element at the E position, and pass all these parameters to the function. And we use the invoke function in order to be conformant to the standard and allow to have functions that could be member functions of a class. The structure is always the same. We need to have index in order to be able to do expansion. And you can see that if we had a way to do this pack expansion that we are looking for, the implementation is much more simple. And it's here that I don't know yet how we will be able to unpack twice. First, I unpacking the product type so that I have a parameter, a pack type, and after that I unpack it. This is syntax that doesn't work in any compiler. We are seeing what can be done. The idea will be that we unpack directly the parameter PT, but we don't know yet how to do that. And I believe that it is towards this kind of things that we should go for C++20. Okay. Another example for swap. Swap of 2 product types. Again, swap implementation, and the implementation, what we do, a swap is a customization point. We introduce the function stdswap, and we will expand this call, the swap function, and for that we are using fold expression expansion. And here the fold expression expansion is used with the comma operator. We are expanding all these expressions, okay, and this expression have no result, and there's no problem. We have this parenthesis, dot, 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 comma. This is a fold expression, and we are accumulating the value, but we don't accumulate anything because there is nothing to accumulate as a result of swap. But we can do that already in C++ 17. Once we have defined this function for all the product types, we have that the current standard that it is limited to tuple-like types could be extended and say that tuple cat will be the same thing that product type cat, but we want to return a tuple. And std apply, there is no reason that we don't have it for all the product types. Make from tuple is a function that constructs a type from the parameters, from the elements of a tuple. We have made a generalization. We have now a type that covers tuple-like CRAs and structs with public members. And you can see on the left the number of constructor and assignment that we have for the std tuple. This is because we are defining interfaces that are too specific. If we allow to be able to construct a tuple from a product type, we have on the right that a lot of functions are working the same. Then we can define, we can have the same functionality with less code. And this is good. We have here that not always we reduce. On the standard, we have some for std pair, we have some constructor, but we don't have the possibility to construct a pair from another tuple or from another product type that has two elements. This is exactly what I am adding here in order to be coherent. And I will do that only for pair and tuple, because these two types are types that have no meaning on the semantics of each one of the elements. Then we are not losing, there is no risk. The single thing that we are having here, I take a product type with two elements, I am naming the first and the second. No problem you don't need more. The opposite, it is not true. We cannot move from a pair to any structure because we have a meaning with the fields. Some algorithms, we are used to think of algorithms that work on heterogeneous containers, in the STL, and the functions that need to be passed to these algorithms are functions that have the type of the container as parameter. But we have here that our container is heterogeneous. That means that our function needs to be in some way overloaded for each one of these types. This is what I have called n functions, because we have n overloads possible. And we need this kind of functions for example, the for each algorithm, which we will do something for each one of the elements of the product type. Or, for example, for a transform function that will apply a function to each one of the elements and return again a product type with the results. Or a fold left. A fold is think of fold is in the standard we talk accumulate. Okay, we are accumulating a specific state with the result of the application of the NF functions to each one of the elements. Then we need this kind of overloaded functions. We can use classical function objects. We can define a structure and overload the operator call. And this is nice. We master what we are doing, and sometimes this is what we will do because we need to I don't know, to store something that it is needed. We have also generic lambdas, lambdas that take the parameters with auto, and this is, you would say, the equivalent of a template. And maybe in C++20, we will have what we call overload set. We'll say a slide for that. And I proposed some time ago to have an overload that takes n functions and construct a function object so that we have the overload for all of them. Different ways, but the same syntax. This is something that we try to have always. Here is how we can define exactly the same pattern. Function parameters, we forward to an auxiliary function with the index. And here we are using initializer list that will take as parameter the expansion of this expression. Then when we do a for each, we expect that the application of the function to each one of the parameter is done on the good order. We expect that we will call first to the 0 element 1, 2, 3. Okay? And initializer list gives us this order. When we call to a function, we don't have this order. The standard don't specify the order of evaluation of the arguments. But for initializer list, we have it. And the expansion is just, well, call to the function f. I should put here, invoke the function f with the name element. And here we are adding comma 0 so that the result of this expression is always of the same type, an integer, and we are able to put it in an initializer list that we just put on the basket. We do nothing at all. We are telling the compiler just do this sequentially in this order. And when we will have the code generated, the assembler, this disappears. There is no assignation at all of nothing. This object don't exist. This is a very simple use of this for each function. And it allows to print each one of the elements of a structure. We have seen some algorithms that work with this kind of types, product types, that provide access to the elements and the size. But we need also to be able to construct some of these types. And these types are very close to an aggregation of values. Then it should be great if any product type can be initialized using an aggregate initializer. This is most of the case. It is like that, okay? But we have not that as requirement for yet for a product type. But I believe that this requirement is needed because we need to be able to initialize things also in a generic way. Another thing is that what we want is to be able to return product types from functions. And not all the product types can be returned. In particular, C arrays cannot be returned from a function. Then C arrays are good. In some cases, there are good cases. I have a legacy code that has a CRA. I need to work with this CRA. How I can do? It is code that I cannot move and change. There are always some reasons. Anyway, don't use CRAs on your code. Use instead stdRA, clearly. This kind of functions, cat, that need to build a new type. We want a result, a new product type, or transform. There are a lot of more. We will see some of them. And we need to be able to construct these types. And we have a proposal, not a proposal, sorry, a C++ 70 feature that allow us to construct a type without giving the template arguments, and these arguments will be deduced from the arguments of the function. Before that, we needed to have, for example, pair, int, string, parentheses, AB. Now we are able to do that without giving the template parameters. Then we have something that allow us to construct a type, a product type, only from his name, independently of the types that are included in. On the slides, the array is on red or orange because it was not clear its array will be supported. And after the last meeting of C++, arrays will be supported. We will need some specific guide to do that, but we'll have. And some time ago, I started to make something that do almost the same thing that we have with template parameter deduction, but at the library level. Okay? Then I believe that this will supersede this, but then I have this factory, generic factory. This generic factory is just a way I can build a type just giving the parameters that constitute this type. It is a good one for pair, for tuple, and for arrays. I have no name for C arrays. Sorry. I have no name for the template array because the template array is a template that has a type and an integer. And the function takes a template with a variable number of types. Then if we were uniform, we will not need to do things like that. And then RITC, TC as type constructor, is a template that will be able to construct from the arguments. There is a proposal, and maybe one day when C++ 17 will be finished, we will have time to review new proposals. This is the template parameter deduction applied to tuple. And here there are some algorithms that need this kind of additional constraint. It's a type, that is a product type, but that it should be, or at least copyable or movable, and have some kind of factory as a make. Then we can transform, we can filter, get only the elements that satisfy some specific predicate. We can drop the first. We can do a lot of things once we are able to construct a type that is similar to the type we are working on. Then if we are able to construct a new type with a single argument, we are able to define the transform function. And once we have that, we have that the type is an enfunctor. I will not. Enfunctor will give us a lot of things that are applicable to the type. If we define the applicative functions and lift, we will be able to define lift because make, it is just lift. I will not enter on the details. This is something that it is just to give you an idea of the kind of things we can do with this kind of types. If we define chain, we will have a monad. If we have make, but we are able to have the construction with multiple arguments, we can define all these things, and this allows to do a lot of things with product types, with structs, because product types are with other structs. Okay. Here there are some of the algorithms that we can find now in Bus HANA. And the product types fall in with the product types that have this make function. We can do all these things. Okay. Then the idea is Bus HANA is there, is a very grateful, useful library, and we need to move it to the standard. And we will do maybe it little by little, step by step, not all at once. And we have more and more. And the other library that works also with this kind of things is Bus Fusion. And here there are some of the algorithms that Bus Fusion have already, and that we could have once we have a generic access to product types, to structure binding types. Okay, last one for transform. And we see on the top that we need the make TC function. And we will overload the transform function. Think about TC as the slide is not good. The class TC, there could be a template class. But think the fact is we can transform a type following a n function and result on the same kind of type. For that, we need that PT is a type constructive type, and we are able to do this kind of transformation. Some basic examples of the use of transform. We can, given a tuple, to get another tuple with the strings of each one of the elements, or given a point, and I don't know how point it is defined. I know it is a product type. Again, I could get, but as I don't know how this, I could request, okay, build a tuple as the result, because I don't know if point is able to construct something as a point B, but instead of integers or floats, to have strings. Okay, I will just end by some examples. When we define hash functions, there is a very sample. We can define a hash function for types that has the same representation, that two suite of bits of O and 1s will represent only the same type. There are no holes. There are no paddings. Then we can define this uniquely represented function that exists on the standard for all the product types in this way. Just we calculate using a for left the size of each of the sum of the elements, and we compare if the size of the type it is equal to the sum. If the sum is equal, there is no hole. The previous thing, what we have do, we have accumulate the size of. Okay? We can first think of transforming the element by his size. The line, and assign it to Q2, and transform and give a product type with the size. And after that, we can do the same. We have a for left, adding these things. And we see that this kind of transformations are quite close to what we have with the range library. That we can use some kind of pipe in order to take a product type as input of a transformation, and we'll have as a result maybe another product type or a result. Then we can think of having this kind of syntax, okay? And here we are using generic lambda expressions with auto, so this could have also a name, okay? And overload sets will allow us to have a name with that. So the code could be even simpler and easy to read. Just the first example, using instead of product type, tuple like access product type, but when we start to play with these algorithms, we see that what we have in order to stream all the things, we are accumulating things on an stream. And for that, we can use the fold left function. But we need an index because the access is now at compile time. I will not, I will let you take a look. Either the two are similar. One is using a function object, the other is using a lambda. And we see that the function, it's having only the code that is needed for a step, because the algorithm takes care already of the end of the. And when we use lambda expression, generic lambda expression, we need to have this kind of DCL type. Give me the type of this argument that it is in some way not so friendly. But anyway, I will not talk much more about. But when we have product types, we know that with the current architectures we have, that working with array of structures, it is not so good, because we have some algorithms that are using CX, and don't use DX and DY. We are losing memory on the cache. And we want to have maybe something different. And then we have in mind something that is an array of structures, but it is located in memory in this way. And it is interesting to be able to move from a description of your type as a product type and have this representation. Then I give you just some pointers. I have not do that in this respect. There is a scattered library, very clean, using boost fusion as tuple-like product type interface. There is also a blog of Jose Maria Lopez Muñoz that make it really simple to move from one to the other. I believe that it is a good blog to read, as the ones of André, of course. There are a lot of things to do just on algorithms, and when we algorithms that build other product types, we are building something else. We are copying, then we can think of algorithms that are lazy, not eager. Then all these things are been doing already for the range library. The same kind of things are applied to this container because the single difference is that we are using metaprogramming. We need the help of the compiler to access these elements. We have also that some product types have names for the fields. We need tags. And we have this kind of tags already for tuples in the range tiers, something that we are working on. Usana is working also on this tagged approach. And just what I say, lazy algorithms will be really something to see if we can gain some performance using them. It is not always clear. We need to check. Conclusion, summary, product types are everywhere. They are rich because they support a lot of, they don't request too much things, so we can do a lot of things with them. And what we need is to decide for the next standard to have one generic access. I don't know which one we will have. We need one. That's all. It's independent. The one. We need to build on them. That's all. Thank you for listening. And
hi. I have an impression that the underlying problem is that we do not really have compile time reflections. If we had them, for instance, we could automatically generate a tuple of elements out of the structure or a tuple of references to element of the structure, leaving aside the bit fields. And perhaps this would actually improve things even better. What do you think?
Yes, but I am saying that we need one interface for that. Here we have reflection. Because it's the compiler that is, it is not giving it maybe through a reflection interface. This is a reflection interface. Product type, size, product type, get, is a reflection interface.
For types solely. For types in structure.
Yes, but this is the kind of types I want to name product types.
There's relatively little missing from that interface that you would want in reflection. Like accessing things by name is probably not something you're going to do in a generic context, and everything else you have, right?
Right.
Functions.
And I believe that the reflection interface will be more than welcome, because we need also to have access to the name when it is present, the name of the field. It is something that people want to explode, to maybe do some logs and give some semantic information.
You should
Yes.
call it Reflections Light, and then everyone would vote for it.
This is less than the reflection library will be there one day. It is a big, very big proposal. I want to be able to work on product types without waiting that the proposal it is on the, because we need just to define the interface. How the compiler implement it is not important. We need an interface. In the slides, you will have the reference of all the things we are talking about. And the first thing is my sandbox for playing with all these concepts.
Yeah, I'm not quite familiar with the generic factories you're using. That's essentially the same as like a templated factory function, but as a constructor, so I can name it the same thing as the type, right?
Yes. For example, when we have a constructor that have the same type, it's okay. It is as a template argument deduction. But for example, for feature, we have already a specific factory make ready feature. We don't have the constructor.
Yeah.
How do we map make feature with this make ready feature? We need to customize. How do we map, for example, for optional, it works without problem because there is already a constructor from the type. There are other types that don't provide a constructor, but they have a factory. And make sure.
Yeah.
Make sure it is better that doing a SharePoint with a new. Then we can take advantage of that. So having always the same syntax. Make on the type constructor and the parameters. Thank you very much for coming and listening.
Big thanks to Vincente Botet.